This is part 2 of the lecture covering static friction. We're going to take a look at a specific example involving this stack of books. I'm going to read the problem here. Go ahead and copy it into your notes. A 4-kilogram book is placed on top of a 5-kilogram book. So I'm going to say if the white book here is 5 kilograms, it's not, but let's just say that. And the blue book here is 4 kilograms like so. Okay, we're given the coefficient of static friction between the two books. That's given to us as 0.6. The system of books is placed on a horizontal frictionless surface. So we are still simplifying the situation here by assuming that the desk is frictionless. Okay, and then we're supposed to find the maximum horizontal force that could be applied to the bottom book such that the books do not slip. Now, here's what I mean by that. Let me go ahead and place the books like so for clarity. And then I'm going to push on the bottom book here with a relatively small amount of force. When I do, the two books do not slip against each other, like so. And they accelerate together to the right-hand side. The question is, however, okay, well, what is actually pushing the top book to the right-hand side? It's not me. Instead, as we'll see, it's the static friction that occurs between the two books. That's what's pushing the top book to the right-hand side. Watch what happens, however, if I push on the bottom book with a large amount of force, like so. Notice that the two books then therefore do slip, and then therefore they would have different accelerations to the right-hand side. That's a different problem. So what we're asked to calculate is the maximum amount of force that I can apply to the bottom book, like so approximately, such that the two books do not slip. Okay? Okay, now let me begin to diagram out the problem in the following way. All right, so here's this surface like so. Okay, the surface is horizontal, and it is frictionless. Okay, at the end of the problem, I'll briefly describe just qualitatively what would happen if we took into account kinetic friction between the desk and the bottom book, but we'll do that at the end of the problem. Okay, then we've got our two books. Okay, now I'm going to call the bottom book here M2. I'm going to call the top book here M1, like so. Okay, M1 is given to us as 4 kilograms, and M2 is given to us as 5 kilograms. And then we're given the coefficient of static friction between the two books. That's given to us as 0.6. Okay, and then what we're going to do is push on the bottom book like so with this force F push. This is going to be our unknown. What we want to do is we want to calculate the value of F push such that static friction at its maximum value occurs between the two books. So we're going to calculate F push such that Fs max occurs. And then the two books will accelerate to the right-hand side with some value A. Okay? Okay, now let's actually begin by taking a look at the forces that are being exerted upon the top book. The blue one, for example, when I do this. How many forces are acting on the top book when I do that? There are 3. They are as follows. Okay, so now we're taking a look at the top book here. We're looking at M1. Okay, first of all, pretty obviously, we have the normal force upwards being exerted upon N1, and then the weight downwards. Okay, there's no acceleration for M1 in the vertical direction, therefore these forces cancel. And then as I said earlier when I was demonstrating this, what force is then acting on the top book in this direction that's causing its acceleration? It's static friction, assumed to be at its maximum value. That is Fs max. Now here's how you can wrap your head around why that is. Not relative to the table, but relative to the bottom book. In which direction does the top book tend to slip? Okay, I'm going to separate the books a little bit so you can see this a little bit more easily. But relative to the bottom book, not the table, in which direction does the top book tend to slip when I do this? It tends to slip in that direction relative to the bottom book. So then therefore preventing that from happening has to be a force of static friction acting on the top book in the opposite direction. Once again, assumed to be at its maximum value. Okay, now let's go ahead and add up the forces here horizontally. When we do, we just have Fs max is equal to M1A. We're given the coefficient of static friction between the two books. So therefore, I'm going to go ahead and write the Fs max here as coefficient times normal force. And now before I go any further, is this normal force the normal force acting on M1, or is it the normal force acting on M2, which we haven't even described yet? It's the normal force acting on number 1. The reason for that is because we're talking about friction between these two surfaces, not between these two surfaces. So this right here is normal force number 1 for that reason. Now we do already know what normal force number 1 is equal to. It's equal to the weight of the top book. So let's go ahead and substitute that into here. Like so. And now you'll notice that the M1 cancels out. And I can now just solve for the acceleration A. So let's go ahead and get that value of the acceleration is the coefficient of static friction multiplied by G. So this is equal to 0.6 times 9.8, which is then therefore 5.88 meters per second squared. Okay? Okay, now let's take a look at the forces being exerted upon the bottom book. Once again, when I do this. Let's see if we can keep track of all the forces. I'm going to have to do this on the lower board. Okay, so now this is for the bottom book M2. We first of all, very obviously, have its own weight, M2G downwards. We also have the weight of the top book pressing down with its own weight, M1G. And then we have the desk pushing up from below like so. This is normal force number 2. Notice that normal force number 2 is not equal to book number 2's weight. It's actually equal to the combined weight of the two books. So N2 is equal to M1G plus M2G. Okay, now there's no friction between the bottom book and the table below, but remember that there is static friction between the two books. The question is, however, is acting on the bottom book, in which direction does that static frictional force point when I do this? It has to point to the left-hand side. Okay, now there's a couple of different ways in which you can think of the Fs max here, like so. The easiest way to think of it is, first of all, in terms of Newton's third law. So if I go back up to the top board for just a moment, recall the following. Remember that M2 pushed on M1 in this direction with this force. Think of that as the action. So then therefore the reaction is that M1 pushes back on M2 in the opposite direction with the same amount of force. That's right here, the Fs max that I just drew. In addition to that, of course, we also have the F push that's unknown to the right-hand side. And that then, of course, in part causes the acceleration A. There's another way, by the way, in terms of thinking of the Fs max. This is a little bit trickier to visualize, but let me ask you the following. Once again, not relative to the desk, but in this case, relative to the top book. In which direction does the bottom book tend to slip when I do this? Relative to the top book, the bottom book slips in that direction. So preventing it from slipping has to be the force of static friction acting on the bottom book in the opposite direction. That's once again this guy right here. So there's a couple of different ways to think of this Fs max. Frankly, the easiest way to think of it is in terms of Newton's third law, as I described earlier. Okay, now let's go ahead and add things up here horizontally. So in this case, we have F push in the same direction as A, and then minus Fs max, and this then equals 2A, like so, the net force being exerted upon the bottom book. Okay, now the Fs max. Remember, it's the same thing as what it was on the top board. That is, Fs max is equal to the coefficient of static friction multiplied by normal force number 1, and normal force number 1 is equal to book number 1's weight. So let's go ahead and substitute that in here. I'll write it out as a couple of steps so you can see it. Once again, take care to note that that's normal force number 1 once again, and normal force number 1 was equal to book number 1's weight. Like so. Clean this up a little bit. There we go. And now the only unknown here is F push, which we now solve for. So this is the maximum amount of force that I can apply to the bottom book such that the two books don't slip. And remember, we already know what the acceleration is. We calculated that earlier in the example. All right, so let's go ahead and plug in. So in the first term, we have the coefficient of 0.6 and then times 4 kilograms times 9.8, plus then 5 kilograms for the bottom book times the acceleration of 5.88 meters per second squared from earlier. This comes out to be 52.92 newtons as the answer. So here's the meaning of this number. If I push on the bottom book with exactly this force, then this happens. Fs max occurs between the two books, and the two books accelerate to the right-hand side at 5.88 meters per second squared. If I push on the bottom book, however, with a force that is less than this value, like so, then Fs max does not occur between the two books, and ultimately the acceleration to the right-hand side is less than 5.88 meters per second squared. However, if I push on the bottom book with a force that is greater than this value, like so, then the two books slip against each other. It's a kinetic frictional situation between the two books, and the two books have different accelerations to the right-hand side. Notice that the bottom book has a greater acceleration to the right-hand side than the top book when I do this, like so. Okay, and then lastly here, just to complete the problem with something that I stated earlier, keep in mind that we are still idealizing the situation somewhat in this problem by thinking of the desk here as being frictionless. What would happen in this problem if we took kinetic friction between the desk and the bottom book into account? Well, if we did, acting upon the bottom book in this direction would be an additional kinetic frictional force vector from the desk below. And then that kinetic frictional force vector would be equal to presumably a coefficient of kinetic friction and then multiplied by a normal force. But which normal force would it be? It would be normal force number 2. And the reason for that is because we would be talking about friction between these two surfaces here, the bottom book and the desk below. So then that kinetic frictional force vector would be dependent upon the normal force N2. Now, I know, of course, that this is a horribly mundane situation. Quite frankly, there's nothing really all that interesting about pushing a stack of objects across the desk like so. But as you can see quite nicely, there's a lot of good basic dynamics that is going on in a problem such as this. Make sure that you study this problem in some detail, okay? All right, that concludes static friction.